Whenever we study projectile motion at what I would call human scale velocities and distances, we make some assumptions that aren't exactly true. One assumption we make is that the gravitational field is constant near the surface of the Earth. And you see that here. I made that assumption when I made this little simulation. The gravitational field is not changing. The other assumption that we assume is that the gravitational field points straight down. So we're essentially assuming that we're on a completely flat surface. The field is pointing straight down. Newton's law of gravitation tells us that if we actually think on a larger scale, neither of those assumptions are actually true. The farther away we get from the center of a mass of a planet, the gravitational field will get weaker. And if we get far enough, it will get significantly weaker. The other thing is, as we move around the planet or across the planet's surface is curved. And so the gravitational field is not pointing straight down like this. It is pointing towards the center of the planet. For our purposes here, we're so many thousand miles above the center of the planet that it pretty much looks like it's down. But once we get to larger scales, these things don't quite hold anymore. So to think about these larger velocities in these larger scales, we've made this little simulation. It's not as cute. Maybe one day we'll put some nice graphics on it so it is. But this is to really model things a little bit more accurately. So what you can do here is you can set a launch angle. You can set a launch speed. The launch angle is in degrees. Launch speed is in meters per second. And also the launch altitude in meters. And then when you hit restart, you will see the little path of the projectile right over there. And you see it's starting to look a little bit different than the paths that you might be familiar with in traditional projectile motion. And we can change a lot of things. The way I've default set this is actually the size and the mass of this object is actually that of the moon. So you can actually think about that we are launching these projectiles on the moon, and it's in a vacuum. We are assuming that there's no atmosphere. And if you want to make the simulation run a little bit faster, you can change this time scale. But the faster you run the simulation, the less accurate it will be. But it will get you pretty close to what the reality is. So let's say we wanted to run it 5 times as fast, so we could put 1,000 right over here. And then when we run it, you see that the entire simulation is running faster. So what I want you to do is really tweak these different things and think about what happens as the projectile gets faster as you might change the angle. So let's say we had a low angle, say a 15-degree angle. So there you go. It kind of launches, but then it hits the planet again. But let's make it go a little bit faster. Let's make it go 1,600 meters per second. And then you see, well, it gets a little bit further. Let's see 1,700 meters per second. And we see that it gets even further than that. And I don't know, let's try 1,850 just to see what happens. 1,850 meters per second. And then when we launch it, you see that it's getting even further still. And you might be wondering, at some point, can I stick this thing to orbit? Or how can I change the launch angle and the velocity so I can change it, put this thing into orbit, and the launch altitude? So right now it's only 10 meters, but maybe I want to make it 10 kilometers. 1, 2, 3. So that would be 10 kilometers. I restart. And it's still hard to see because this thing is the size of the moon. But you see here, it looks a little bit different now. I can change the launch angle once again. I can actually go to a much lower launch angle. And now when I launch it, I can see all sorts of interesting things. And if you want to actually change the scale of this entire thing, you go right over here to meters per pixel. So right now, each pixel on my canvas represents essentially 25 kilometers. So there's a couple of things to think about. First of all, do projectiles, when you really take Newton's law of gravitation into consideration, do they really travel in parabolas? And if you don't think they're traveling in parabolas, what would describe their path? The other thing that's fun to think about is just how, based on the altitude, the initial launch angle, how can you launch a projectile into orbit? How can you actually get it to do what it's doing here? And what are the conditions where this happens, and when does it not? And also change the time scale, because you'll see that some of this change in the path right over here, it might be due to error introduced due to the simulation. It's not an absolute perfect simulation. We have to pick some time scale. So as you lower the time scale, think about what's happening to the simulation, although it will take longer to run. The other thing that you might want to do is pick a certain altitude, set your launch angle to 0 and see what velocity you need, what launch speed you need actually, to get your thing to go into orbit. And see how that actually relates to the distance from the center of mass and the gravitational field at that altitude. So hope you have some fun with this. Let me do another. Actually, it would be fun actually to do a high angle. So let's do a high angle, and let's do a relatively lower velocity, 1,000 meters per second, which is still quite fast, about the speed of a bullet. So let's say, so that's actually not that interesting. Let's make it 1,500. 1,500. So that's a little bit more interesting. What if we made the launch angle really steep? So you can see this is kind of fun. So you can launch it at an even steeper angle, just like that. Anyway, hopefully you have fun with the simulation and it makes you think a little bit more about maybe the assumptions you used to make about projectile motion.